All right, let's start with so-called rank theorems. The first one is about immersions. All right, here is the statement. Let F be a differentiable map. Differentiable map. Map. And P is a point in M, so that if it's an immersion at P, then one can find coordinate neighborhoods around P in M and f of P in N. Say the coordinate neighborhoods are phi1 from U1 up to V1 and phi2 from U2 up to V2, where P is in U1 and that lies in M. F of P is in V2, no, U2, that's in N. Yes, and V1 is an open subset in Rn, Rm, and V2 is an open subset in Rn. Open subsets. So that we have the following picture. Here is, let's say, U1 in M, and I have the map F here, and this goes into U2, which is a subset of the manifold N, and I have the coordinate neighborhoods or coordinate systems phi1 and phi2 into, let's say, V1, which lies in Rm, and this goes into V2, which lies in Rn, and here I have the function f hat, which is just phi1 inverse f and then phi2. Okay, and the statement is the following. This function phi2 f phi1 inverse on the point x1 to xm is given as follows. X1 to xm, and then we have zeros. So the first m coordinates are x1 to xm, and the rest are just zeros. Okay, so that's the statement. So in other words, we can find coordinate neighborhood so that our function f in this coordinate systems looks like just the standard immersion. Okay, so any immersion is actually standard under a suitable coordinate system. That's the statement. All right, so let's say f tilde, which is this composition, has coordinate functions f1 up to fm. Here, each fi is a function of course, m variables, and it's a function from Rm into R. Okay. And by assumption, you know, this function is an immersion at the point P. Therefore, the rank of the derivative of f hat has is m at that point. Since uh, uh, f hat, sorry, f is an immersion at P, f hat has rank m at phi 1 of P. Okay. All right. So let me write it this way: f hat phi 1 of P. Okay. This is just what the coordinate functions of f are these. Oh, sorry, I made a mistake. I have n of those, not m, because it is a function from Rm into Rn. So I have n many functions. Okay, now the Jacobian of this is just the following matrix: del f1, del x1, and del f1, del xm, and then I have the same thing for f1, f2, up to fn. So fn del xm. Okay, so this is an n by m matrix evaluated at the point f phi of p. All right. Okay. Now this matrix has rank m, and it has n columns. Therefore, all the columns are linearly independent, and it has n rows. And n is larger than or equal to m because it's an immersion. Uh, so this means what? M of these rows are linearly independent. Of course, the linearly independent ones do not have to be the first M of them, right? It might be the second one and then the fifth one, so on, right? But by interchanging the coordinates yi's, here uh, I guess didn't tell you, but let's say here we have the coordinates x1 up to xm, and here I have coordinates y1 up to yn. Coordinates on Rn and coordinates on Rm. By permitting the coordinates yi's, these coordinates, I may assume that the first n rows of this matrix are linearly independent, because permitting the coordinates is equivalent to permitting fi's, because here the coordinates on Rn y1 to yn, so these are y1, y2, yn. So if I permute the coordinates, this means I actually change this coordinate system by another diffeomorphism. By interchanging or permuting the coordinates, I get another coordinate system, a diffeomorphism here. Let's say, I don't know. Okay, H, and then I have another coordinate system. So this is a diffeomorphism which interchanges this coordinates yi's, and I obtain, let's say, v2 tilde, another one. So let me write this down. The row rank of the above matrix is M, and thus uh, by permuting the coordinates by i's, or equivalently f i's, we may assume that the first m rows are linearly independent. Okay. Well, so I assume from now on that I have n rows, but the first m of them are linearly independent. All right. Now we define another differentiable map. Let's say g hat from Rm cross. So I add some extra coordinates here, so that the total number of coordinates is equal to the dimension of the domain is equal to n, and it goes up to n. It goes to Rn, given by this formula: g hat of uh, okay, g hat of x1 up to xm, and then I add some new variables, xm plus 1 up to xn, and uh, the function is as follows. Here I have f hat x1 up to xm, and then I add to this the following. I have zeros, and then this new coordinates xm plus 1 up to xn. Okay. All right. So this is equal to what? This is equal to following: g x1 up to xn is equal to f1 x1 up to xm up to fm x1 up to xm, and then in the remaining ones, maybe I should write like this because it won't, space is not enough. F1 f2 up to fm, And then I have fn plus 1, but here I have this extra xn plus 1. So, and here I have fn, and then I have xn. So the original map f was f1 up to fn. After the empty place, I just add the coordinates xm plus 1 and so on. Okay. Well, if you do this, then the Jacobian of this, then the Jacobian of this function at this point becomes what? Let's see. Here, uh, I will take again derivatives of all these functions with respect to n variables, x1 up to xn. Uh, Derivative of f1 up to x1, and then here I go up to derivative of f1 up to xm, and then derivative of f1 with respect to xm plus 1. But this fi's, all of them are functions of x1 up to xm, right? So they are not functions of the remaining variables m plus 1, xn plus 1 up to xn. Therefore, the derivatives of fi's with respect to xn plus 1, xn plus 2, xn are all zeros. So these are all zeros. And then similarly, I have del f 2 and so on up to del fm, del x1, del fm, del xm, and then I have zeros here. Okay. All right. And then I have what? Fm plus 1 derivatives of this, all the with respect to all the variables. So these are just some numbers. We don't know what they are. No, I have to be careful. Up to xm, there are some numbers, but after xm plus 1 and so on, fm plus 1 has no xm plus 1 in it. So derivative of this with respect to xm plus 1 is 0. But I have this extra term here, and the derivative of this with respect to xm plus 1 is 1. Therefore, the derivative of the mth coordinate of g hat with respect to xn plus 1 is 1, and then derivative with respect to other variables are 0. And then I have again some stars here, and then for xn plus 2 I have 0 and then 1, and then again zeros like this. So it goes like this up to the last coordinate. So I have here just some ones, and I have this matrix. So this is an n by n matrix, n by n matrix, and here I have the m by n matrix, which is non-singular. This is the square matrix and non-singular. And here I have the identity matrix. So this matrix is just identity matrix of size n minus m. Yani bu n eksi m çarpı n eksi m'lik identity matris. Burada da f tildanın Jacobian'ı var. Onun ilk n m row'u ve ben ne biliyorum? Bunlar lineerle bağımsız bu row'lar. Burada da identity matrisi var. Dolayısıyla bu matris invertible bir matris. Çünkü determinantını aldığınızda işte bu kare matrisin determinantı çarpı bunun determinantı, o da 1 olacak. Dolayısıyla bu invertible bir matris artık. Okay. Okay. So note that since the first m rows are linearly independent. Neden? Because I know that here these the first m rows of this matrix are linearly independent, and the first m rows of those are just these gadgets. So they are linearly independent, and here I have the identity matrix. We see that the Jacobian of this gadget, I guess this should be phi 1, right? Yes. Okay. Is invertible. Well, G hat is a function from actually not from Rm, it's a function from well, a subset of Rm. It's a function from U1 cross Rn, but this is a subset of Rm. So it's a function from locally Rn to Rn, and its Jacobian is invertible at phi 1p. Therefore, by the inverse function theorem, G hat is a local diffeomorphism. Okay. Okay. Since the G hat is an isomorphism, by the inverse function theorem, G hat is a local diffeomorphism. So there are some open sets at around the point P or phi 1p, and its image, so that G hat here is a diffeomorphism. All right, now so here I have, let's say, some open set in Rn, and I have another open set in Rn, and I have this G hat, and it's a local diffeomorphism, meaning that it has an inverse, and the inverse function is also differentiable. Okay, now we have the following picture. We have the picture. Okay, I have, let's say, the manifold M here, and then I have the function f, and I go up to the manifold n, and here I have the point p, and this is the point f of p, I have the coordinate system into Rm, and this is phi 1p, an open subset actually in Rn. And then I have here f hat, and here I have Rn, and this is uh, f hat of phi 1p. All right. And here uh, I have this map. I compose uh, this function with the inverse of g, which is also a diffeomorphism. Again, this goes into Rn. Here I had phi 2, and this map is just what? Phi 2 and then G inverse. So G inverse composition with phi 2. All right. Now, this is another coordinate system. Instead of phi 2, I have this coordinate system. And I claim that this map here is the required map. So what is this? F tilde composition G inverse. Okay, this is so I have the coordinate phi 1 and then phi 2 tilde, phi 2 tilde, and using this coordinates we will see that the map F looks like the standard immersion. Let's see if it is the case. Here I have coordinates x1 up to xm here, and this is mapped under f hat to f1 up to f n. Okay, and then this is mapped under G inverse to G inverse of f1 up to fn. Okay, now let's write this again more carefully. Here actually I have x1 up to xm. Uh, okay, yeah, let me. What was g? G was the following: x1 up to xm, and then m plus 1 up to xn, and this is sent via g into f1 up to fm, fm plus 1 plus xm plus 1 up to fn xn, and I have here of course the inverse map going in the reverse direction, and from this I can write the following: finally since g of x1 xm 000 is equal to f1 up to fm, fm plus 1 up to fn, because I choose this coordinate 0, so this is 0, this is 0. I have just fn plus 1 up to fn. Okay. Since this is the case, we have uh, G inverse of f1 x1 up to xm. So G inverse of this expression, f2 x1 up to xm, or let me write not f2, fn x1 up to xm. What is this? G inverse of this is of course this gadget. So it is x1 up to xm and then all zeros. And this is actually what we wanted to prove, because we wanted to prove that uh, you know, x1 up to xm is mapped to G inverse composition with f, and G inverse composition with f at x1 to xm is equal to this expression. Hence we have this gadget is equal to, right, this is equal to x1 up to xm, and then the rest are zeros. So exactly this uh, gadget, and this finishes the proof. Okay, now this proves the fact that any immersion is actually standard under a suitable change of or choice of coordinates. A similar result holds for submersions. Namely, we have the following theorem. Submersion. Okay, let f m to n be a differentiable map, and p is a point in m, so that f is a submersion at p. Then we can find coordinate neighborhoods as in the above theorem. So that uh, phi2 composition f, şöyle yazayım. So phi2 composition f, phi1 inverse x1 up to xn xm. This time m is larger because it's a submersion, and this is given as follows. You just take the first n coordinates, okay, at all points of the domain of not domain, range of phi1, the coordinate function for the first manifold. Okay, next we have a definition. I will not prove this, but the proof is similar. This time you have to increase the dimension of the range. Okay, in the first theorem, we increased the dimension of the domain, right? Namely, we multiplied U1 with some extra copies of R so that it became an open subset of Rn, and G hat became a diffeomorphism, a local diffeomorphism, and we used that to obtain the required coordinate function. This time you have to do this on the range space, okay, because its dimension is n and less than m, so you have to multiply this by some okay, actually by this gadget, sorry, m minus n, and do something similar. Okay, all right, so I will not do this, leave it as an exercise. Here is an important definition. An embedding is a one-to-one one-to-one immersion f from m to n, which is a homeomorphism of n into m. So what I mean by this, that is a homeomorphism into something, means the following. F is a homeomorphism of n onto its image uh, n tilde, okay, with its topology as a subspace of uh, M. Okay. The image of an immersion of an embedding is called an embedded submanifold. Okay. Here is what we mean. So we have a manifold and then the function f into some other manifold, and this is the image of f, let's say, which is n tilde. Okay, and f from n into n tilde, this is a subspace of M, uh, and it's a homeomorphism. Homeomorphism onto n tilde, of course, and n tilde has the relative topology inherited from the topology of M. Okay. Uh, well, let's see whether the examples we have considered earlier are embeddings or not. We had, namely, sorry. Okay. First, we had this. Uh, this is an immersion because when you take derivatives, okay, Okay. So let me do it this way. Uh, Here's f. Neredeydi f? Şu fonksiyon, right? When you take the derivative of this, you will get sine here and cosine here. Cosine 2 times t minus pi. And this f tilde. So let me write that actually gadget. So f tilde of t is minus 2 times sine t minus pi over 2, and then 2 times cosine 2 times t minus pi over 2, and this is never 0. Okay, therefore f is an immersion. The derivative is never 0. So it's from dimension 1 dimensional space into 2 dimensional space, and it has full rank. Therefore f is an immersion. But not an embedding. Embedding because I already wrote that actually. Yeah, this is an immersion. I don't need to write this. I already wrote. F is an immersion, but not an embedding. Since F is not one-to-one. Right? F is not one-to-one. Therefore, it cannot be an embedding. An embedding has to be a one-to-one immersion, which is a homeomorphism onto its image. This map is an immersion, and it is one-to-one. G is also one-to-one, but it is not an embedding or embedding, since G is not a homeomorphism onto its image. Neden değil? Bunu birçok nedenden söyleyebiliriz ama şöyle de diyebiliriz. G homeomorfizm değil. Çünkü bu uzay eğer homeomorfizm olsaydı bu uzay kompakt değil. Not compact. Ama görüntüsü, yani bu n not compact ama n tilde compact. Dolayısıyla G bir şey olamaz. Homeomorfizm olamaz görüntüsüne. G sürekli, yani sürekli bir fonksiyon, birebir görüntüsüne örten ama inverse'ü homeomorfizm değil. Okey. Evet, bugünlük de bu kadar olsun. Arkadaşlar. Görüşmek üzere, hoşça kalın.